Hello everyone. This is lecture number 2 of Ionic equilibria. In the previous lecture we have seen what are electrolytes, the different types of electrolytes, strong electrolytes and weak electrolytes. We have seen the different concepts of acids and bases. Now in today's class we are going to learn the ionization constant of an acid, ionization constant of a base. My name is Arpita and you are watching Arpita classes. Let's get started. So, ionization constant of an acid. Give a heading, ionization constant of an acid. Let's see what is it. Any acid can be denoted as HA. We need to start writing acids this way now. Why we are writing HA? Because suppose an acid is HCl. So H stands for H only and A is the anionic part of the acid. So we start writing acids as HA. So that acid, if it dissociates, it will give you H plus and A minus in the in the aqueous solution. Okay, it gives you H plus and A minus. Now, if you try to write down the equilibrium constant for this reversible reaction, it will be K is equal to concentration of H plus into concentration of A minus divided by concentration of HA. This is the definition of an equilibrium constant. For any reversible reaction, the equilibrium constant is the product of the concentration of the products divided by the concentration of the reactant. Now, this equilibrium constant, when we talk about an acid, a dissociation of an acid, then the equilibrium constant is called as ionization constant of an acid. So this equilibrium constant only called as ionization constant, and for an acid it is denoted by Ka. Okay. Now for strong acids we are not going to talk about Ka. Why? Because suppose for a strong acid HCl, when HCl dissociates it gives you H plus and Cl minus. I have given a unidirectional arrow because this is a strong acid. If you try to write down the ionization constant for this, it will be concentration of H plus into concentration of Cl minus divided by concentration of HCl. Now consider, initially we consider 1 mole of HCl. So initially there is 0 mole of H plus and 0 mole of Cl minus. After some time, the HCl will completely dissociate and you will get 0 mole of HCl and 1 mole of H plus and 1 mole of Cl minus. So if you put this concentration values here in the equilibrium constant, concentration of HCl becomes 0 and anything divided by 0 is not defined. That means for a strong acid, the K value is so large that we cannot define it. So we will not talk about the strong acids. In this chapter, we are going to talk about the weak acids. So we have seen the ionization constant of an acid is Ka is equal to concentration of H plus into concentration of A minus divided by concentration of Ha. It means that more the concentration of H plus, larger will be the value of Ka and stronger will be the acid. More is the concentration of H plus, since H plus is in the numerator, so more the concentration of H plus, larger will be the value of Ka and stronger will be the acid. If you understood this concept, let us do one question out here. Arrange the following acids in the order of increasing strength. Arrange the following acids in the order of increasing strength. You have been given some acids over here and the Ka values. Okay. Let us take the first acid is HF and the Ka value is given 3.5 into 10 raised to power minus 4. Next acid is HCN. The Ka value is 4.9 into 10 raised to power minus 10. Next one is acetic acid, CH3COOH. Ka value is 1.7 into 10 raised to power minus 5. And last one is HNO2. The value is 4.5 into 10 raised to power minus 4. We have to arrange these acids according to their increasing strength. Yes. So first of all, you can see the order. This is 10 raised to power minus 4, this is 10 raised to power minus 10, this is 10 raised to power minus 5, and this is 10 raised to power minus 4. So this is the smallest value of Ka. Therefore, this acid is the weakest acid. So first we'll take HCN. Next will be 10 raised to power minus 5. So that is your acetic acid, CH3COOH. Now we have two acids of the same order, 10 raised to power minus 4 and 10 raised to power minus 4. So see the magnitude, this is 3.5, this is 4.5. So this is the lesser value, HF into 10 raised to power minus 4. HF is 3.5 into 10 raised to power minus 4. So next will be HF and last will be your HNO2. So here we can see the maximum value of Ka is of nitrous acid, and nitrous acid is the strongest acid here. So we conclude here that more is the value of Ka, larger the value of Ka, stronger the acid would be. Let us now talk about the ionization constant of a base. So give the heading ionization constant of a base. We will write the base as MOH, where M stands for the metal. Suppose it is NaOH, so M stands for the metal and OH is hydroxyl group, okay? So we'll write down the base like this. If the base dissociates, definitely it is a weak base. It will give you M plus and OH minus. Now, if I try to write down the equilibrium constant for this reversible reaction, it will be K is equal to concentration of M plus into concentration of OH minus divided by concentration of MOH. This equilibrium constant for a base is known as ionization constant of a base, and it is denoted by Kb. So Kb is the ionization constant of a base. Now from this expression we can understand that more the concentration of OH minus, if the OH minus concentration is more, that means the value of Kb will be higher, which also means stronger is the base. Stronger is the base. So Kb value is high, that means the base is strong in nature. Let us try to conclude this with an example. Say you have arranged the following bases in order of their increasing strength. Okay, and you have been given here some bases and their Kb values. The first base is NH4OH, ammonium hydroxide. The Kb value for this is 1.7 into 10 raised to power minus 5. Next is CH3 whole twice NH. This is dimethylamine. Kb value is 5.4 into 10 raised to power minus 4. Next is C2H5 whole thrice N, triethylamine. And the Kb value for this is 6.4 into 10 raised to power minus 4. So we have to arrange them in the order of increasing basicity. So let us see what is the lowest value of Kb. This is 10 raised to power minus 5, this is 10 raised to power minus 4, this is 10 raised to power minus 5. So among these two, NH4OH is having the lesser value. So NH4OH is having the least Kb value. Next will be C2H5 whole thrice N, that is triethylamine, and the last one will be diethylamine. So among these three, we understand that dimethylamine is the stronger base. So we conclude that more is the value of Kb, higher is the value of Kb, more stronger the base will be. So far we have understood what is ionization constant of an acid, what is ionization constant of a base. So for a weak acid, if the acid dissociates in a reversible condition and you take the equilibrium constant of an acid, that is only called as the ionization constant of an acid, denoted by Ka. In the similar pattern, if a weak base dissociates and you try to find out the equilibrium constant of a base, the equilibrium constant of a base is called as ionization constant of a base, which is denoted by Kb. Now we are going to learn one law which is known as Austwal's dilution law. Let us see what the law says. It is Austwal's dilution law. The law says that the degree of dissociation, DOD means it is degree of dissociation, which is denoted by alpha, of a weak electrolyte is directly proportional to the extent of dilution. It is directly proportional to the extent of dilution, or you can also write down it is directly proportional to the square root of dilution. So now what do you understand by this? Let us take an example. Achha, here one more thing is there. In some books you are going to get the word ionization, and in some book you are going to get the word dissociation. Now these two words are same only. Ionization word we use, ionization, degree of ionization or degree of dissociation. Both of them are same. Ionization word we are used for polar covalent compounds. Just write it down. Degree of ionization, this we are using for polar covalent compounds, and dissociation word is used for the ionic compounds. Okay, so if you get degree of dissociation or degree of ionization, the meaning is same. Degree of ionization is used for the polar covalent compound, degree of dissociation is used for the ionic compounds. Now let us take one example over here. We are taking an example of HA acid, weak acid, dissociating into H plus plus A minus. Okay. Achha, what the Austwal law says, the degree of dissociation of a weak electrolyte is directly proportional to the extent of dilution. Degree of dissociation is denoted by alpha. Alpha is directly proportional to the square root of dilution. This is the mathematical expression for the Austwal dilution law. Let us prove this. Suppose we have a weak acid HA which is dissociating into H plus and A minus. Now initially we have 1 mole of HA. So this is 0 and this is 0 at the initial condition. Now suppose at equilibrium, number of moles we will calculate. Now suppose the degree of dissociation is alpha. Now what does alpha mean? From 1 mole, alpha is getting dissociated. Okay. Degree of dissociation is alpha means from 1 mole, alpha mole is getting dissociated. So at equilibrium, how many moles of HA will be remaining? It was initially 1, alpha got dissociated. So remaining moles at equilibrium will be 1 minus alpha for HA. Now see, from 1 mole of H plus is formed. So if alpha dissociated, so alpha of H plus will be formed. So when it is getting dissociated alpha, see again here from the equation we can see from 1 mole of H plus is formed. So from alpha mole of H plus will be formed. So at equilibrium, how many H plus will be remaining? Alpha. And same thing, how many A minus will be remaining? Alpha. So these are the number of moles at equilibrium. Now let us consider the concentration at equilibrium, because we need the concentration at equilibrium to find out the equilibrium constant. Consider the entire volume of the reaction where you are carrying on the reaction, the entire volume of the vessel is V. So the concentration would be number of moles upon volume. So it will be 1 minus alpha upon V for HA. This will be alpha by V and this will be alpha by V. So these are the concentration at the equilibrium constant condition. Now let us find out the equilibrium constant or ionization constant of an acid. Ka is equal to concentration of H plus into concentration of A minus divided by concentration of Ha. Now put the concentration terms. H plus is alpha upon V. So put it here, alpha into V, alpha upon V. A minus is also alpha upon V divided by, this is 1 minus alpha upon V. So calculate this. This is coming alpha square upon V square divided by 1 minus alpha upon V. So now calculate alpha square upon V square into, V will go up and 1 minus alpha, V and V square will get cancelled. So you are getting alpha square divided by V into 1 minus alpha. Now since we are talking about the weak acid, here the value of alpha with compared to 1 will be very less, because weak acid means they will be dissociated only 4%, 5%, 3%, 2%. That means the value of alpha will be 0.05, 0.04. Okay, so it will be very less as compared to 1. So we can neglect the value of alpha. So we can write it down this way. I'll just write it down. We can write it down that Ka is equal to alpha square upon V. We neglected alpha from here because alpha is very small as compared to 1. Okay, so Ka is equal to, we got alpha square upon V. So alpha square is equal to, we are getting Ka into V, or alpha is equal to root of Ka into V. Now we all know that Ka is constant for a particular at a particular temperature. So you can take this as constant. So it will be alpha proportional to square root of V, which is your Austwal dilution law. So we have seen that Austwal dilution law says that the degree of dissociation is directly proportional to the square root of dilution. We have taken an example of an acid and we have proved the Austwal dilution law. Austwal dilution law can also be alternatively said as the degree of dissociation of a weak electrolyte is, we said it already earlier, we had said that it is directly proportional to the square root of dilution, or we can say it is inversely proportional to the square root of concentration. Now what do you mean by this? Alpha, that is degree of dissociation, is directly proportional to square root of dilution, or it is inversely proportional to the square root of concentration. Now we need to prove this part. Okay, let us take the same acid again, Ha giving you H plus and A minus. Now we are considering the initial concentration. In the previous case we took the initial number of moles. Now we are taking initial concentration. So initial concentration, you consider this as C, this is 0 and this is 0. Alpha being the degree of dissociation, at equilibrium, what will be the concentration? At equilibrium, concentration is C minus C alpha. See why this is. Alpha is the degree of dissociation. That means that 1 mole of the acid liberates alpha or dissociates alpha amount, alpha moles. So if C mole will liberate C alpha. So how much will be remaining? C minus C alpha. Again listen, from 1 mole dissociation is alpha. So from C, what is the dissociation? C alpha. So initially there was C, concentration was C, and now C alpha got dissociated. So how much is remaining? C minus C alpha. This is the concentration of the acid at equilibrium. Concentration of H plus will be C alpha. Because from 1 mole of H plus is dissociated. So from C alpha mole of H plus will be dissociated, and A minus also will be C alpha. Now try to write down the equilibrium constant, which is concentration of H plus into concentration of A minus divided by concentration of H. This is C alpha into C alpha divided by C minus C alpha. Let us further simplify. This is C square alpha square divided by Take C common from here. It will be 1 minus alpha. C and C square gets cancelled. So we get C alpha square divided by 1 minus alpha. This is Ka. Now, the same concept, since alpha is very less than 1, so we can neglect this value. So we can directly write down Ka is equal to C alpha square, since 1 minus alpha is very less than 1. Or you can just say alpha is very less than 1. So we can neglect alpha and we can write down Ka is equal to C alpha square. From here, we get alpha square is equal to Ka upon C. Right? So alpha is equal to root of Ka upon C. Now Ka is constant, so we can remove the equal to sign and Ka. So it will be alpha square is inversely proportional to root over of C, which is this one. Okay, so this is your Austwal dilution law, which is stated as the degree of dissociation of a weak electrolyte is directly proportional to the square root of dilution, or it is inversely proportional to the square root of concentration. So far, we learned the topic of degree of dissociation, ionization constant of an acid, which is denoted by Ka, and ionization constant of a base, which is denoted by Kb. Now let us solve some numericals based on these topics. Our first numerical is the dissociation constant of CH3COOH is 1.8 into 10 raised to power minus 5 at 298 Kelvin temperature. So dissociation constant of an acid is denoted by Ka. The value of Ka is 1.8 into 10 raised to power minus 5 at 298 Kelvin. This is given to us. Calculate its degree of dissociation. So degree of dissociation we have to calculate, which is denoted by alpha. Alpha we need to calculate, and H3O plus concentration. We also need to calculate H3O plus concentration in its 0.1 molar concentration, where the concentration is given 0.1 molar concentration. And also it is given that root over of 18 into 10 raised to power minus 5 is equal to 1.3 into 10 raised to power minus 2. This particular value we are going to use for some calculation. Now let us solve it by the formula. We can solve it in two methods, by directly using the formula of Austwal dilution law, or by solving the entire thing. So both methods I will show you. Okay, so first we are going to use the formula, and the formula says that alpha is equal to root of Ka upon C. If you see Austwal dilution, from Austwal dilution law we got this formula. Okay, so alpha is equal to K upon root over of K upon C. Alpha we have to find out. Ka, value of Ka is given 1.8 into 10 raised to power minus 5. Value of C is also given 0.1 under root of this. So if you calculate this, it will be 18 into 10 raised to power minus 5, and the value of 18, root of 18 into 10 raised to power minus 5 is 1.3 into 10 raised to power minus 2. So the value of alpha, we get this. Okay. Now we need to find out the concentration of H3O plus. Now to get the concentration of H3O plus, we have to see the dissociation and see what is it. So let us do the dissociation of acetic acid. CH3COOH dissociates to give you CH3COO minus and plus H plus. Okay, now suppose you take initial concentration as C. Initial concentration is C. This is 0. This is also 0. At equilibrium, we are considering that alpha is the degree of dissociation. So from 1 mole, alpha gets dissociated. From C mole, C alpha will get dissociated. This is important. From 1 mole of CH3COOH, 1 mole of CH3COO minus and 1 mole of H plus is obtained. From C mole, C of this and C of this will be obtained. Now, alpha dissociating means is degree of dissociation alpha means from 1 mole alpha gets dissociated. So from C mole, C alpha will get dissociated. C mole means C molar. Concentration is C molar. From C molar, C alpha will get dissociated. So if C alpha is getting dissociated, how much is remaining at the equilibrium? How much is remaining? CH3COOH, this molecule. How much is remaining at the equilibrium? It is C minus C alpha which is remaining. Now see, from C From 1 mole of H plus is obtained. We have to find out the concentration of H3O plus. So we have to see this one. So from 1 mole we get, from C mole we get C mole. So from alpha we'll get C alpha. If C alpha dissociates over here, C alpha will be formed over here. So the concentration of H3O plus is C alpha. So we can write it here, C alpha. The value of C is 0.1, alpha is 1.3 into 10 raised to power minus 2. So it will be 0.13 into 10 raised to power minus 2, which is 1.3 into 10 raised to power minus 3 molar. So the value of H3O plus is coming 1.3 into 10 raised to power minus 3 molar. This is the answer. So this type of sum we can directly use Austwal dilution law and we can get it. Also at the same time, if you continue from here, then also we should get, let us see. So from C minus C alpha, this is the concentration of acetic acid at equilibrium. C alpha amount of acetate ion and C alpha amount of H plus ion is formed. Now let us write down the Ka for this. It is concentration of CH3COO minus concentration of H plus divided by concentration of CH3COOH. Now let us put the concentration which is there in the equilibrium. CH3CO minus C alpha. This is also C alpha and this is C minus C alpha. So here we get C square alpha square. From the denominator we take C common. So 1 minus alpha. C square and C gets cancelled. So we get alpha square divided by 1 minus alpha. Alpha is very small as compared to 1 because it is a weak acid, and I told you earlier that weak acid they get dissociated only 4%, 5%, maximum 5%, less than 5%. So the value of alpha is 0.05, which is very less as compared to 1. So we can ignore this. So we can just write down it is only alpha square. Okay, so it is only alpha square. We have C also here because only 1 square is cancelled. So it is C alpha square. We are neglecting 1 minus alpha. So we are neglecting alpha since alpha is very small as compared to 1. So we got Ka is equal to C alpha square, or alpha square is equal to Ka upon C, or alpha is equal to root of Ka upon C. So we can show the entire thing and then we can use the values over there, get the answer, or you can directly use the Austwal dilution law and you can get the answer. So this way we have to solve the numericals. Please copy it down. Let us solve another numerical based on the same concept. They are saying calculate concentration of OH minus in 0.01 molar solution of NH3 if the Kb value is 1.76 into 10 raised to power minus 5. And there is something given so that the calculation becomes easy. So under root of 176 into 10 raised to power minus 5 is 4.2 into 10 raised to power minus 2. This is given to you. Let us solve this. NH3 dissociates in water to give you NH4 plus OH minus. Okay. So this is the equation dissociation of NH3. We are considering initial concentration of NH3. Initial concentration of NH3 C. Water we will not take because we know that water is constant, so we neglect water. Initial concentration of NH4 plus and OH minus is 0. We consider the degree of dissociation of ammonia is alpha. So concentration at equilibrium. Concentration at equilibrium. Now if the degree of dissociation is alpha, from 1 mole alpha gets dissociated, or from 1 molar alpha gets dissociated. From C molar, C alpha will get dissociated. So how much is remaining at the equilibrium? It is C minus C alpha. Now from 1 mole is formed. This also 1 mole is formed. So C alpha dissociates. So this is C alpha formed and this is also C alpha formed. Now we will write down the expression for Kb. Kb is concentration of NH4 plus into concentration of OH minus divided by concentration of NH3. We will again not take the concentration of water because it is taken as constant. So now concentration of NH4 plus, which comes C alpha. This is also C alpha. Down we have C minus C alpha. Further calculation we will get C square alpha square. Down C common 1 minus alpha. this C and one of the square gets cancelled. So we get Kb is equal to C alpha square upon 1 minus alpha. Now I told you that alpha is very small as compared to 1, so we can neglect it. So we get Kb is equal to C alpha square, or alpha square is equal to Kb upon C, or we get alpha is equal to root of Kb upon C. So we got this. Now we can put the values. Value of Kb is coming 1.76. They have given this value 1.76 into 10 raised to power minus 2, and the concentration is given 0.01 molar. So put it here, 0.01 molar. Now we will calculate this. It will come 176 into 10 raised to power. This is 1 upon 100. So that 100 will go up. 1.76. Minus the value of this is 10 raised to power minus 5. I'm so sorry. This is 10 raised to power minus 5. Okay, yeah. Now this is coming point and point removes from here. So 176 into 10 raised to power minus 5, which is given, that is 4.2 into 10 raised to power minus 2. So this is the value of alpha we got. Alpha is equal to 4.2 into 10 raised to power minus 2. What they are asking, concentration of OH minus. Now see what is the concentration of OH minus. It is C alpha. So write down here concentration of OH minus, which is C alpha. So C is your 0.01 and alpha we got 4.2 into 10 raised to power minus 2. So finally we get 4.2 into 10 raised to power minus 4. This is this much molar. So this is the answer for this particular sum. So what you can do is you can show the dissociation, you can go till here and then you can put the values, or you can directly use this formula because we already derived this formula in Austwal dilution law, and we can put the values and we can get the answer. But I will suggest you start from here, show the dissociation and do the entire sum. So far we found out the ionization constant of an acid, and the acids were monobasic acids. Or we found out the ionization constant of a base which were monoacidic base. What if we have dibasic acid or tribasic acid or triacidic base, diacidic base? How to find out the equilibrium constant for them? Because in those cases, the acids or bases do not dissociate in one step. For example, suppose we have monobasic acid. Examples of some monobasic acids are, say, HCl, HNO3, HF, HI. These are all monobasic acids which will dissociate in one step. So we can get the ionization constant for them. What about if I have a dibasic acid? Let us see the examples of dibasic acid. Suppose we have H2SO4, H2PO4, H2SO3, H2CO3. These are all dibasic acid. These are also called as diprotic acid, okay? Or we have tribasic acids. For example, we have H3PO4, H3PO3, H3BO3. These are all triprotic acid or tribasic acid. How to find out the ionization constant for dibasic or tribasic acid? Let us take some example of tribasic acid and I'll show you how to do that. So let us take the example of H3PO4. Directly I am taking tribasic acid. Now H3PO4 is a very strong acid. So in the first step, it will dissociate into number of steps. In the first step, it will only liberate one H plus to give you H3O plus, and because we are dissociating in presence of water, so the liberated H plus will react with water to give you hydroxoniamine. And the remaining anion will be H2PO4 minus. One hydrogen is removed from here, so the remaining part is H2PO4 and it will contain a negative charge. Now, the Ka value for this will be very high because this is a strong acid and it will completely dissociate. Now once you get this anion, in the next step, this anion will get dissociated. H2PO4 minus will get dissociate now. Now the dissociation will be slow and it will be a reversible process because this is a weak acid. Why this is a weak acid? It already contains a negative charge. So removing one positive charge which contains a negative charge from the species which already contains a negative charge, from there you are trying to remove one positive charge will be difficult. So that is why it will dissociate, but it will dissociate slowly and it will act as a weak acid. It will give you one more H plus is removed, so it will give you HPO4 2 minus. Suppose the equilibrium constant for this step is Ka2, and in the third step now this species will come here HPO4 2 minus, and it will again dissociate. This is again a weak acid, much more weaker acid than this also, because now it contains two negative charge, so removing H plus is very difficult from here. But if you do this step, one more H plus is removed and finally you will get PO4 3 minus, and suppose the dissociation constant for this step is Ka3. So we have taken a tri-basic acid, we have done the liberation of 1,1H plus, so we liberated or we eliminated all the H plus from the acids in 3 different steps, and for each and every step we got the equilibrium constant as Ka1, Ka2 and Ka3. Now if you do the net reaction, if you see the net reaction, what is basically happening here, so you will see this H2PO4 minus and this H2PO4 minus will get cancelled here, this and this will get cancelled, so you get H3PO4 in presence of water will give you 3 hydroxonium ion and PO4 3 minus. This is the final net reaction, and suppose the Ka value for this net reaction is Ka. So Ka will be obtained as Ka1 into Ka2 into Ka3. This expression is experimentally found out that if an acid is dissociating into number of steps, not in a single step, so this can be done for dibasic or tribasic acid. Both of the acids will be following this same pattern. So if they are dissociating into number of steps and each step has got their own equilibrium constant, then the overall equilibrium constant for this will be Ka1 into Ka2 into Ka3. That is a product of the equilibrium constants of each and every steps. Copy down. The way we got the ionization constant of a tri-basic acid, in the similar pattern we can get the ionization constant of a tri-acidic base or diacidic base as well. So let us take one example of tri-acidic base, aluminium hydroxide, and see how to find out the ionization constant of the base. So let us take aluminium hydroxide, which can be dissociated as, now the first step will be unidirectional arrow because it is a strong base. It will dissociate to give you AlOH whole twice plus and OH minus. Since it is a base, one hydroxyl group will be liberated. So one of the hydroxyl group is liberated as OH minus. So the entire remaining species will be AlOH whole twice and it will carry a positive charge. Now AlOH whole twice, this species is a weak base because it is already containing a positive charge, so it will be difficult to remove one more hydroxyl group from here. So it will behave as a weak base and it will give you AlOH 2 plus when one more OH minus is liberated from here, and finally AlOH 2 plus will again act as a weak base. It will give you Al3 plus and one more OH minus is liberated from here. So this is a triacidic base which is dissociating into 3 steps. This is your step number 1 and we are considering the equilibrium constant for this step is Kb1. Okay. This is step number 2 and the equilibrium constant for this step is Kb2, and this is step number 3. The equilibrium constant for this is Kb3. Okay. Now we will see the net reaction. If the reaction happens in one step, what is the reaction? This L plus this and this will get cancelled, this and this will get cancelled. In the net reaction, aluminium hydroxide will dissociate to give you aluminium 3 plus and 3 OH minus, and suppose the net reaction ka equilibrium constant or ionization constant is Kb. So we can get Kb as Kb1 into Kb2 into Kb3. So remember, for dibasic acid, tribasic acid, or for diacidic base or triacidic base, we get the ionization constant by taking the product of the ionization constants of each and every step. Now, you might be observing that sometimes I say equilibrium constant, sometimes I say ionization constant, sometimes I say dissociation constant. All these words are same only. They mean the same thing. Only thing is that the equilibrium constant for an acid is given a special name, that is ionization constant of an acid. Equilibrium constant of a base is ionization constant of a base. Okay. Similarly, equilibrium constant of water is called as ionic product of water. So all of these have the same expression as a expression of equilibrium constant. That is the product of the concentrations of the product divided by the product of the concentrations of the reactants. Only thing is that for different species, we have given different name. Dissociation constant for ionic compounds, ionization constants for polar covalent compounds, ionization constant for acids, ionization constant for bases, and so on. So this is the concept of ionization constant, dissociation constant, Austwal dilution law, the numericals involved in that. Now we will move on to the next topic, which is ionic product of water. So we'll start with ionic product of water. Ionic product of water, which is also called as ionization constant of water. As I told you, these all are same only their different names are given to them. So here we are going to take water molecule, one more water molecule. We'll consider one of the water molecule will liberate hydrogen or will donate hydrogen. So this H2O, which is donating hydrogen, is converted into OH minus, and the donated hydrogen is taken by this H2O to give you H3O plus. So one of the water molecule is acting as acid, the other one, which is taking proton, is acting as base. We are aware of acid-base concept, Lorry as Bronsted concept. Okay. Now, this way, when water dissociates, two molecules of water dissociates to give you H3O plus and OH minus. Among these two molecules, one is acting as acid, one is acting as base. This process is called as autoprotolysis of water. This is autoprotolysis of water. Proton matlab proton, lysis matlab breaking. So proton ka transfer ho raha hai, so this is called as autoprotolysis of water. If we try to write down the equilibrium constant, it will be concentration of H3O plus into concentration of OH minus, product of the concentration of the products divided by product of the concentration of the reactants. So concentration of H2O into concentration of H2O. So we can write it H3O plus concentration into OH minus concentration. In the denominator, we have 2 times H2O, so we can write it as H2O to the power 2. Now see, concentration of H2O is, it doesn't change because H2O is, there are many molecules of H2O. Okay, so concentration of H2O will hardly change because it acts as a solvent and many molecules are there. So that is why we will take this whole thing as a constant. H2O whole twice as a constant. So take this also this side along with K and say this entire thing is a constant, this one. Okay, so this is equal to, we are getting H3O plus and OH minus, and we are giving a name to this constant, which is your Kw is equal to H3O plus into OH minus. This Kw is called as ionic product of water. Okay, Kw is known as ionic product of water. Note it down that Kw does not depend, it does not depend on the initial concentration of water. Initial concentration of water. How much water you are taking initially, you are taking 1 mole or you are taking 100 mole or you are taking 1000 mole, it doesn't matter to Kw. Kw does not depend on that. So what is the factor on Kw? Depends is the temperature. So temperature is the only factor. Kw depends on temperature. Temperature is the only factor on which Kw depends, and it has been found out that the value of Kw is equal to 10 raised to power minus 14 at 25 degrees Celsius or 298 Kelvin. Please write it down. This is very, very important. We are going to use this value many times. The value of Kw is 10 raised to power minus 14 at 25 degrees Celsius or 298 Kelvin temperature. Now this value is given in each and every book, but remember that if we change the temperature, the value of Kw will be changing. Okay, so note it down. So the value of Kw does depend on the temperature. So it has been found out experimentally that at 63 degrees Celsius temperature, when the temperature is increased, the value of Kw is 10 raised to power minus 13. See, the value of Kw is also increased. It has increased from 10 raised to power minus 14 to 10 raised to power minus 30. At 11 degrees Celsius temperature, when the temperature is down, the value of Kw has been experimentally found out 0.3 into 10 raised to power minus 14. So the value of Kw is decreased at lower temperature. That means it proves that at higher temperature, if the temperature is increased, the value of Kw is also increased. If the temperature is decreased, the value of Kw also decreases. Okay, so the value of Kw is directly proportional to the temperature. Write down, this is a very, very, very important conclusion. I'll just write it down here because it's not seen over here. Kw is directly proportional to temperature. This is a very important conclusion. Now, understand that any solution which is neutral or acidic or basic, we say that any neutral solution whose pH is 7, less than pH solutions are acidic, more than pH solutions are basic. Actually, any solution which is neutral, what happens there? The concentration of H3O plus and the concentration of OH minus is equal over there. That is the reason the solution becomes neutral. Okay, pH is 7 is not a proper statement to say because pH can vary. The pH for neutral solution can vary. It is not always 7. It depends on the temperature. Yes, we always say that pH is equal to 7. In many books it is written because we consider the value of Kw 10 raised to power minus 14 at 2298 Kelvin. But if you change the temperature, the Kw value will change and hence the pH also will change. We'll talk about all these things. So understand that any solution which is neutral, H3O plus and OH minus concentrations are equal. Okay? Any solution which is acidic, concentration of H3O plus will be greater than concentration of OH minus. Any solution which is basic, concentration of H3O plus will be lesser than concentration of OH minus. This is a proper statement to make. Now see, for a neutral solution, what do we say? We say that concentration of both of them are equal. Okay. So, and we also found out Kw equal to concentration of H3O plus into concentration of OH minus. Now, if you talk about 298 Kelvin temperature, the value of Kw is 10 raised to power minus 14. And there, since we are talking about neutral solution, both the concentrations are equal and say we are taking them as X. Concentration of H3O plus is also X and OH minus is also X. So we get X squared is equal to 10 raised to power minus 14 or X is equal to 10 raised to power minus 7. That means that in a neutral solution, OH minus concentration is also 10 raised to power minus 7 and H3O plus concentration is also 10 raised to power minus 7 but at 298 Kelvin temperature. Okay, so this is one important conclusion we got, that at a concentration which is for a neutral solution, both concentrations are equal and at 298 Kelvin temperature, both concentrations will be 10 raised to power minus 7 for a neutral solution. So if it is acidic solution, for acidic solution, what will happen? Concentration of H3O plus will be greater than 10 raised to power minus 7, and for basic solution, concentration of H3O plus, we will just see H3O plus only, which is less than 10 raised to power minus 7. So understand that the concentration of H3O plus or OH minus individually can vary, but when you multiply them, The products should come 10 raised to power minus 14 at 298 Kelvin temperature. The product will not vary. It is constant. But the individual concentration of H3O plus and OH minus will vary, and that is why you get different types of solutions, acidic, basic or neutral solutions. So we got the concept of ionic product of water. We also have seen when the solution becomes neutral, acidic or basic. So remember that neutral solution means the concentration of H plus and OH minus is equal. We do not say pH of neutral solution is 7. Yeah, it is there in the book, but it is not a very right statement because pH can vary as Kw can vary with temperature. Hence, pH also can vary with temperature, and hence the neutral solution ka pH can vary. It is not always same. So, neutral solution means the concentration of H plus and concentration of OH minus is equal. Acidic solution, concentration of H plus is more. Basic solution, concentration of OH minus is more. Now, if you talk about at 298 Kelvin temperature, then we have found out that concentration of each component for a neutral solution has to be 10 raised to power minus 7 mole per liter or molar. Okay, concentration unit has to be taken always as molar or mole per liter. For an acidic solution, concentration of H3O plus will be greater than 10 raised to power minus 7 molar, and for a basic solution, concentration of H3O plus will be lesser than 10 raised to power minus 7 molar. This much thing we have already done. Now let us see one numerical. The numerical says find the concentration of H3O plus and OH minus for a solution of a weak acid HA whose Ka is 2 into 10 raised to power minus 8 and 8 moles of acid are present in 1 liter of the solution. So let us see this numerical. HA is the acid. It is a weak acid, so it will dissociate as H plus and A minus. Now you are considering initial moles. Initial moles, they are saying 8. So you take 8 moles as the initial moles. This is 0 and this is 0. We are considering the degree of dissociation is alpha. So moles at equilibrium will be how much? Moles at equilibrium. Initially 8 mole is present. 1 mole, from 1 mole alpha gets dissociated. So from 8 moles 8 alpha gets dissociated. So how much HA remains at equilibrium? 8 minus 8 alpha. Okay. How much this is formed? From 1 mole is formed. So from 8 alpha H plus is formed and 8 alpha A minus is also formed. Now we will write down the equilibrium constant for the acid. Ka is equal to concentration of H plus into concentration of A minus divided by concentration of HA. Now take the concentration terms. H plus is how much? 8 alpha. Okay. This is moles at equilibrium. We have to find out the concentration at equilibrium. This is a big mistake. Please correct it. We have found out moles at equilibrium. We need to actually find out concentration at equilibrium because in Ka expression mein we have concentration terms, not the mole term. This is the square bracket means it is a concentration. Okay. So find out the concentration. Concentration means mole per volume. Okay. So concentration at equilibrium. Concentration at equilibrium. Now moles is 8 minus 8 alpha and 1 liter is the volume of the solution. So 8 minus 8 alpha upon 1. This is 8 alpha upon 1 and this is also is 8 alpha upon 1. Now since this is 1 liter, so there will be no problem because, but you remember this, okay, it is a concentration now. So H plus is here 8 alpha, OH minus is also 8 alpha and HA is coming 8 minus 8 alpha. So it is 8 into 8, 64 alpha square divided by 8 common 1 minus alpha. Cancel it out. This is coming 8 alpha square. From 1 minus alpha, we can neglect alpha as alpha is very, very small. So we get Ka is equal to 8 alpha square. Okay. Ka is equal to 8 alpha square. So alpha square is equal to Ka upon 8. So alpha is equal to root of Ka upon 8. Now let us put the value of Ka. It is 2 into 10 raised to power minus 8 divided by 8. This is getting cancelled. 1 by 4. 1 by 4 means 25 upon 100. We can write 25 upon 100. So that 100 will go up. So it will be 25 into 10 raised to power minus 10. So you take it out of the root. So it will be 5 into 10 raised to power minus 5. This is the value of alpha we got. 5 into 10 raised to power minus 5 is the degree of dissociation of this weak acid. What they're asking, concentration of H3O plus. See what is the concentration of H3O plus? H plus and H3O plus is same. So concentration of H3O plus is 8 alpha. So write it down, concentration of H3O plus is equal to 8 into alpha. 8 into 5 into 10 raised to power minus 4. So this is 40 into 10 raised to power minus 4, or we can say 4.0 into 10 raised to power. We are taking a point out here. Yeah, so it is minus 3 molar. Okay. Concentration of H3O plus is 4 into 10 raised to power minus 3 molar. We have to find out concentration of OH minus also. Now, how to get OH minus? There is no OH minus over here. Now, we are going to use the concept of ionic product of water. Okay. So, we will do that. Please copy it down. Then we will start with that part also. The next part, that is concentration of OH minus. How to find out this. Please copy it down. For the second part now, we have to find out the concentration of OH minus. Okay. So that we will get from ionic product of water. Ionic product of water Kw is equal to concentration of H3O plus into concentration of OH minus. We know this. Now the value of Kw is constant at 298 Kelvin. If nothing is given, we will by default consider the temperature is 298 Kelvin. Okay. So 10 raised to power minus 14, I will put it here. Concentration of H3O plus, we just got it, and the value of concentration of H3O plus is 4 into 10 raised to power minus 3 into concentration of OH minus. So from here we can get concentration of OH minus, which is 10 raised to power minus 14 divided by 4 into 10 raised to power minus 3. Now see, 1 by 4 means 0.25. So it is 0.25 into minus 3 goes up. So it will be 10 raised to power minus 11. So if I shift the point over here, 2.5 into and multiplying by 10, so it will be 10 raised to power minus 12. Yeah, I shifted the point over there, multiplied by 10 at the same time. So 2.5 into 10 raised to power minus 12 molar is the answer for concentration of OH minus. Let's solve one more numerical based on the same topic. They are saying that if a weak base MOH whole twice, now this is a diacetic base, has Kb 1.6 into 10 raised to power minus 8 at 298 Kelvin. Find concentration of OH minus and H3O plus in a solution having 2 molar concentration of the base. So let us take the base MOH whole twice and see the dissociation of it, how it dissociates. It's a weak base, so reversible arrow. It gives you M2 plus and 2OH minus. This is the dissociation. Initial concentration, we will consider initial concentration as 2 molar. This is 0 and this is 0. Let us consider the degree of dissociation is alpha. So at equilibrium, the concentration will be, now see, from 1 mole or 1 molar alpha gets dissociated. So from 2 molar, 2 alpha will get dissociated. So how much the base will remain? 2 minus 2 alpha. From 1 molar M2 plus is formed. So from 2 alpha molar M2 plus is formed. So this will be 2 alpha. Now look at here. From 1 molar, 2 molar OH minus is formed. So when this dissociates as 2 alpha, this will be double, 2 into 2 alpha, that is 4 alpha molar of OH minus is formed. This is important. See again, from the equation 1 molar gives 2 OH minus. So when it is 2 alpha dissociated, it will be 2 into 2 alpha, that is 4 alpha of OH minus form. This is important, okay. Now we are going to write down the Kb value. Kb value is M2 plus concentration OH minus whole to the power 2. The stoichiometric coefficient will go to the power in equilibrium constant, we know that, divided by concentration of MOH whole twice. This is the expression for Kb, okay. M2 plus concentration into OH minus to the power 2. Why 2? Because the stoichiometric coefficient goes to the power in taking equilibrium constant, and divided by concentration of MOH whole twice. Now put the concentration terms. M2 plus is 2 alpha. This will be 4 alpha to the power 2 divided by, this is 2 minus 2 alpha. Now this is 2 alpha into 16 alpha square. Down we can take 2 common, so 1 minus alpha. 2 and 2 gets cancelled. Okay, so what we are getting, 16 alpha cube divided by, from 1 minus alpha we can neglect it. So just we are getting 16 alpha cube. Kb ka value is 16 alpha cube. Therefore alpha cube will be is equal to Kb upon 16. Now let us put the value. Kb is given as 1.6 into 10 raised to power minus 8. So 1.6 into 10 raised to power minus 8 divided by 16. If you remove this point, then it will be 1 into 10 raised to power minus 9. So alpha cube we are getting, alpha cube is 1 into 10 raised to power minus 9. So alpha will be cube root of 1 into 10 raised to power minus 9, which will be 10 raised to power minus 3. So this is alpha. The degree of dissociation is coming as 10 raised to power minus 3. We have to find out concentration of OH minus, which is 4 alpha. So put the value now. Concentration of OH minus is equal to 4 alpha. So that is 4 into 10 raised to power minus 3, and the concentration is taken in molar. So we got this. Now we have to get the concentration of H3O plus, which we will not get from the equation. We will get it from ionic product of water. I am doing it this side. We know Kw is equal to concentration of H3O plus into concentration of OH minus. Since the temperature is mentioned 298 Kelvin, so the value of Kw is 10 raised to power minus 14 is equal to concentration of H3O plus and concentration of OH minus. We just got 4 into 10 raised to power minus 3. Therefore, concentration of H3O plus is 10 raised to power minus 14 divided by 4 into 10 raised to power minus 3. Now, 1 by 4 means it is 0.25. 10 raised to power minus 14 plus 3 will give you 10 raised to power minus 11. So, I'll put the point 1 digit after. So, 2.5 into. So, it will be 10 raised to power minus 12 molar. This is the concentration for H3O plus. So children, we have to do the numericals based on the ionic product of water this way. If any electrolyte is given, it is a base or it is a weak acid, you can get concentration of one of the component. If it is a weak base, you can get concentration of OH minus from here, and then you have to use the ionic product of water to get the concentration of the other component. Copy down. So far you understood what is Ka, what is Kb and what is Kw. Now we are going to see the relationship between Ka, Kb and Kw for a conjugate acid-base pair. So give the heading relation between Ka, Kb and Kw for a conjugate acid-base pair. This relationship will be applicable only for conjugate acid-base pair. I hope everyone remembers what is conjugate acid-base pair. Just for an example, I told you last time, suppose HCl is dissociated into H plus and Cl minus. So you can see HCl is dissociated into Cl minus by donating hydrogen. So HCl acts as the acid. On the other hand, if you see the reverse reaction, I should write H plus on the arrow so you will understand this better. If you see look at the reverse reaction, Cl minus will take H plus to convert into HCl. So Cl minus act as the base, and these two are called as conjugate acid-base pair. This we have already studied in Lorry-Bronsted concept. Now, today we are going to see the relationship between Ka, Kb and Kw for a conjugate acid-base pair. Let us take an example. I am taking the example of ammonia dissolved in water. Okay. So when ammonia dissolved in water, what do you get? You get NH4 plus and OH minus. Can we write down the Kb for this? Kb for this will be concentration of NH4 plus into concentration of OH minus divided by concentration of ammonia. This is the Kb for this. We will not take concentration of H2O. Earlier I said that concentration of H2O is almost constant, so we will not take that. So this is the Kb for this particular reaction. Now you do the reverse reaction for this is the base here, so this will be the conjugate acid. So now we are going to see the reaction for the conjugate acid, where NH4 plus reacts with water to give you NH3 plus H3O plus. Let us write down the Ka for this reaction. Ka will be is equal to concentration of NH3 into concentration of H3O plus divided by concentration of NH4 plus. This is the Ka for this reaction. So these NH3 and NH4 plus are the conjugate acid base pair. We have written the Kb value for this reaction. We have written Ka value for the reverse reaction. Now we also know that Kw is equal to concentration of H plus into concentration of OH minus, or you can also write concentration of H3O plus into concentration of OH minus. This already we know. Now just multiply these two equations. This is your equation number 1, this is your equation number 2. Let us do 1 multiplied by 2. So 1 multiplied by 2, so that is your Kb into Ka. Let us write the value. Kb is what? NH4 plus into OH minus divided by NH3. Now write down Ka. Ka is this concentration of NH3 into concentration of H3O plus divided by concentration of NH4 plus. Now see what all things are getting cancelled from here. NH3, NH3 gets cancelled. NH4 plus and NH4 plus gets cancelled. So we get only OH minus into H3O plus. And what is this? This is the expression for Kw. So what is the relationship we get? We get Ka into Kb is equal to Kw. This is the relationship between Ka, Kb and Kw for a conjugate acid base pair. So for a conjugate acid base pair, we got Ka into Kb is equal to Kw. From here we can write Ka is equal to Kw upon Kb. Now we all know that Kw is constant at a given temperature. So we get Ka is inversely proportional to Kb. What does it mean? This gives an important conclusion. It means that if the Ka of an acid is more, Kb of the conjugate base will be less. This is only for the conjugate acid base pair, remember. If the Ka of the acid is more, then Kb of the conjugate base will be less. That means a conjugate, if the acid is strong, the conjugate base will be weak. And vice versa. If the base is strong, the conjugate acid will be weak. What does it mean? Suppose if I tell you, I am giving you a strong acid, then the conjugate base will be a weak base and vice versa. If I give you a strong base, then the conjugate acid will be a weak acid. This is the conclusion from here, and if you understood this type of questions can be given to you. Which is more basic? Which is more basic? They have been given Cn minus and HSO4 2 minus. And you have to find out which one is more basic. So let us see, Cn minus has come from where? From HCl. The conjugate, this is the acid, and the conjugate base of HCl is Cn minus. We already know that HCl is a weak acid. If HCl is a weak acid, the conjugate base will be strong. On the other hand, HSO4 minus, 2 minus has come from where? HSO4 minus, sorry, not 2 minus, HSO4 minus. So HSO4 minus, if the hydrogen is added here, you will get H2SO4, right? HSO4 minus, you get H2SO4, the conjugate acid. This is a base. The conjugate acid of this is H2SO4. And we know that this is a strong acid. So if this is the strong acid, then this will be the weak base. So if you are given to compare between these two, then this is the strong base and this is a weak base. Because this has come from a strong acid. The conjugate base of a strong acid will be weak and the conjugate base of a weak acid will be strong. So here if you compare between them, then Cn minus is more stronger base than HSO4 minus. So we have seen the relationship between Ka, Kb and Kw for a conjugate acid base pair, and we have come to a very important conclusion that if the acid is strong, then the conjugate base will be weak, and if the base is strong, then its conjugate acid will be weak. Right, yeah. So now we will come to the next topic, and that is pH of a solution. So let us give the heading pH of a solution. Now we already know this, that pH of a solution, if 7, then we call that solution as a neutral solution. If the pH value is less than 7, we call it as a acidic solution, and if the pH value is more than 7, we call it as a basic solution. Now from where this thing comes, that we have to see today. We will understand today why the pH is less than 7, it is acidic, more than 7, it is basic, and equal to 7, it is neutral. So let us understand the definition of pH is negative logarithm of hydrogen ion concentration. pH is defined as the negative logarithm of hydrogen ion concentration. You can also write negative logarithm of hydroxonium ion concentration, because we already know that whatever is hydrogen ion, we can replace it by hydroxonium ion. But in both the cases, the concentration has to be taken in mole per liter or molarity. The concentration has to be in mole per liter or molarity. Now, let us take an example. They suppose give you that find pH of a solution which has H3O plus concentration as 10 raised to power minus 3 moles per liter. So the H3O plus concentration is given to us, and we have to find out the pH of the solution. So that means here it is H3O plus is given to us 10 raised to power minus 3 moles per liter. So what will be the pH? pH is equal to minus logarithm of H3O plus concentration. Put the value of H3O plus concentration, that is minus logarithm of 10 raised to power minus 3. And we know that log of a to the power n is what? Log of a to the power n is n log a. We know the property of this log's property. So it will be minus of minus 3 log 10 to the base 10. Log 10 to the base 10 is 1. So it will be minus plus 3. So pH of the solution will be 3. So this is how, if the concentration of H3O plus or H plus is given to us in mole per liter or in molarity, we can find out the pH of the solution. Okay, so you understood what is the pH of a solution? pH of a solution is a negative logarithm of hydrogen ion concentration or hydroxonium ion concentration. If we are given hydrogen ion concentration, we can find out the pH of a solution. Now we all know that if the pH of a solution is less than 7, we call the solution as acidic. pH is greater than 7, we call it as basic. Now from where this is coming? We also have learned Kw is equal to concentration of H3O plus into concentration of OH minus. Now the value of Kw is constant at a constant temperature, and that is 10 raised to power minus 14 at 298 Kelvin temperature. It is constant. So we will consider the value of Kw is constant only, because normally the temperature is 298 Kelvin only. And for a neutral solution, concentration of H3O plus is equal to the concentration of OH minus. This also we have seen earlier, right? So if that is so, we consider that the concentration of both of them is X. Put it here in the equation, it will be Kw, that is 10 raised to power minus 14 is X into X, that is 10 raised to power minus 14 is X square. So the value of X comes 10 raised to power minus 7. That concludes that in neutral solution, concentration of H3O plus would be equal to concentration of OH minus, and that is equal to 10 raised to power minus 7. So for a neutral solution, let us find out the pH. pH is equal to minus logarithm of H3O plus concentration, and for a neutral solution, H3O plus concentration is coming 10 raised to power minus 7. Put it here, 10 raised to power minus 7. This is to the base 10. So it is coming minus of minus 7 log 10 to the base 10. Log 10 to the base 10 is 1. So we are getting pH is equal to 7. This is how we get pH is equal to 7 for a neutral solution. Remember, pH is equal to 7 for a neutral solution we say, but that is not always true, because if you change the temperature, the value of Kw would change and accordingly pH also would change. That also I will show you, but normally in our syllabus the pH will always come 7 for a neutral solution, because the Kw value is 10 raised to power minus 14 at 298 Kelvin temperature. That we consider and do everything. That is why pH is equal to 7 will come. But I will show you how the pH will change if you change the temperature. Hence the Kw value changes and the... Now let us talk about an acidic solution. If we are taking an acidic solution, we know that concentration of H3O plus is greater than concentration of OH minus. So in that case, concentration of H3O plus would be anything greater than 10 raised to power minus 7, right? Because in neutral solution, both the concentrations are equal and each concentration comes out to be 10 raised to power minus 7. When we are talking about acidic solution, concentration of H3O plus will be greater than OH minus, and hence it will be greater than 10 raised to power minus 7. So if it is greater than 10 raised to power minus 7, it could be anything 10 raised to power minus 6 or 10 raised to power minus 5 or 10 raised to power minus 4 or anything. Okay. Now let us take the concentration, let us take any concentration of H3O plus, like let us take 10 raised to power minus 4. Okay, 10 raised to power minus 4. I am taking this concentration. So in that case, what will be the pH value? Minus logarithm of H3O plus concentration. Put the value of H3O plus concentration, and that we are taking as 10 raised to power minus 4. Minus 4 you take it this side. So it is log 10 to the base 10. So it is coming pH is equal to 4. So that is how for a neutral solution pH will come 6, 5, 4, 3, 2, 1 and so on. That is the reason pH is always less than 7 for an acidic solution. Now let's find out the pH for a basic solution. So for a basic solution, concentration of H3O plus is less than concentration of OH minus. Hence it will be less than concentration 10 raised to power minus 7. 10 raised to power minus 7, less than 10 raised to power minus 7 can be 10 raised to power minus 8, 10 raised to power minus 9, 10 raised to power minus 10 and so on. So let us take any of the value. Concentration of H3O plus is equal to say 10 raised to power minus 11 suppose. Okay. So what is the pH of this solution then? Minus logarithm of H3O plus concentration, and we have taken H3O plus concentration as 10 raised to power minus 11. So it will be minus of minus 11 log 10 to the base 10, which is coming 11. So that is how pH values are greater than 7 for the basic solutions. So now we understood why the pH value is equal to 7 for a neutral solution, less than 7 for the acidic solutions, and greater than 7 for the basic solutions. Now let us talk about the two extreme conditions. We have Kw is equal to concentration of H3O plus into concentration of OH minus. We know that the value of Kw is 10 raised to power minus 14 at 298 Kelvin temperature. We are considering that we have all H3O plus concentration only and there is no OH minus concentration. That could be one extreme condition where we have complete H3O plus concentration, that is 1, and OH minus concentration is, in that case it will be 10 raised to power minus 14 because the concentration of H3O plus becomes maximum over here and OH minus concentration is minimum over here. In this case, pH of the solution will be what? This is the most acidic condition you can consider. This is the most acidic solution. Most acidic solution. So for this, pH is equal to minus logarithm of H3O plus concentration. So that will be minus logarithm of 1 and log of 1 is 0. So minus 0 is 0. So pH value will be 0 when the solution is maximum acidic in nature. The pH value will come 0. On the other hand, another extreme condition is we will consider now H3O plus is very less and OH minus is maximum. So when OH minus is maximum it will be 1 and H3O plus will be 10 raised to power minus 14. Let us find out the pH of this solution. Minus log of H3O plus concentration and now the H3O plus concentration is minus 14. So minus log of 10 raised to power minus 14. So here it comes minus of minus 14 log 10 to the base 10 and therefore it is coming 14. So this is the most, where should I write? Most basic solution. Most basic solution. So we have the pH scale which ranges from 0 to 14. The pH value will be 0. Then we are talking about the most acidic condition. pH value comes 14. That means we are talking about the most basic conditions. Okay, so from here we can conclude that for acidic solutions, the pH could be 0, 1, 2, 3, 4, 5, 6. For neutral solution, pH is equal to 7, and for basic solutions, pH is 8, 9, 10, 11, 12, 13 and 14. So this is our conclusion. Now, as I told you that pH depends on temperature. This depends on temperature. Why? Because Kw depends on temperature. Okay? Let us see one example. Say at 63 degrees Celsius, experimentally the value of Kw is found to be 10 raised to power minus 30. Okay? So let us find out the pH. We will prove how pH depends on the temperature. At 63 degrees Celsius temperature, Kw is equal to 10 raised to power minus 13. It has been found out experimentally. जो कि normally 10 raised to power minus 14 at 298 Kelvin. But at 63 degree, 298 Kelvin is 25 degrees Celsius. So when you increase the temperature, the value of Kw increases. Now let us see. So for a neutral solution, now what will happen? For a neutral solution, we can write Kw is equal to concentration of H3O plus into concentration of OH minus. At 63 degrees Celsius, Kw has come 10 raised to power minus 13. For a neutral solution, we know that each concentration is equal. So we will take this as x, this is also x. So 10 raised to power minus 13 is x square. So x is equal to 10 raised to power minus x square is equal to 10 raised to power minus 13. So from here we get x is equal to 10 raised to power minus 6.5. Okay. So we get each concentration is equal to 10 raised to power minus 6.5. Now let us find out the pH. pH is equal to minus logarithm of H3O plus concentration. And what is the H3O plus concentration we got? 10 raised to power minus 6.5. This is concentration of each of the ions. Okay, so this is coming 10 raised to power minus 6.5, which is minus 6.5 log 10 to the base 10. So which is coming 6.5. So you can see pH is coming 6.5 for a neutral solution when the temperature is raised. So that is the reason I am telling you, in the book or in our syllabus, pH we will always say 7 for a neutral solution, but remember that pH depends on the temperature. as Kw depends on the temperature and Kw increases with temperature, decreases with temperature. So I proved you that pH depends on the temperature. So for being a neutral solution, the main criteria is concentration of H3O plus and concentration of OH minus has to be equal. So in today's lecture we have seen ionic product of water. We saw the numericals based on that. We have seen pH of a solution, how the pH varies from 0 to 14 and why the solutions are acidic, basic and neutral. Now in tomorrow's class or in the next lecture we are going to see the numericals based on this, numerical based on the pH values and then common ion effect. Thank you so much. पढ़ाई करते रहो.